Hello students, welcome back. We completed everything except for the last example here. And let's study this. It has three parts. Prove that the residue class group Zm has a subgroup of order D if and only if D divides M. Well, M is the order of the original group, and the order of the subgroup always divides the order of the original group. Remember that? Lagrange's theorem? So one direction is trivial. Now, if D divides M, can we always find a subgroup here? Well, that's your challenge. And it's not going to be too bad because Zm is a cyclic group. So you can find a nice generator, and that's it. Okay, here we go. Step 1, this is really trivial. Due to Lagrange's theorem, the order of the subgroup must divide the order of the original group. In this case, D divides M. So one direction is trivial. The other direction, if D divides M, then can we always find a subgroup of order D? Well, if D divides M, then M divided by D is an integer, and you can use that integer. So D divides M, then M is D times some Q. Yes, Q for the quotient. You see, division algorithm goes like this, but there's no R. So M is dQ, and D divides M, so M is dQ, and Q is M over D. And this Q satisfies all our demand. So the residue class given by this Q, or the subgroup generated by this Q bar, the cyclic subgroup generated by this Q bar, has precisely D elements here. 0Q, 1Q, 2Q, all the way over to D minus 1Q. And then you see all these are unique. Yes, we went through all those way back in lesson 3, I think, when we did cyclic groups. Now, is this a subgroup? Yeah, everything was done. By the way, if you don't like this Q expression, you can use just M over D expression too. Even though this looks like a fraction, it's an integer. Okay, all right. Those are quick. Now let's go to the second part. Prove that Zm has only one and only one subgroup of order D for each D that divides M. So previously, in order to be a subgroup, D divides M, of course, but also whenever D divides M, there is a subgroup of order D. We got up to that, but part B is saying there's only one. So we have to prove that this one here, we established this one. Or if you don't like this Q expression, just use M over D. That's the only one. How do you prove that? Suppose that there's something else, and then of course everything must be cyclic because the starting group is cyclic, and we know that every subgroup of a cyclic group is cyclic. So we have to have a generator, and that generator versus Q, that's something to think about. Okay, let's begin. Suppose that there is a subgroup R bar generated by R bar of order D. And remember, Zm is a cyclic group, so every subgroup has a generator. So the generator in this case is R. And then R has order D, and D divides M, so M over D is some quotient Q, which is an integer, positive integer, because everything is positive here. We are dealing with order, so all positive. And as you saw before, this Q or more precisely speaking, Q bar will generate a cyclic subgroup of order D. And we have to prove the uniqueness. There is one and only one subgroup. So this subgroup generated by R bar and the subgroup generated by Q bar must be the same. See the idea? See where we are headed? So let's make this observation. D times R bar is 0 bar. Why? Because the order is D. And in non-abelian case, we use power expression and we add E, but this is abelian, so we use repeated addition expression, so we use coefficient expression. So this is R bar plus R bar plus R bar repeated D times, and that should be 0. And if you use modulo operation, dr is congruent to 0 modulo m, or divisible by m. And what do we have? dr is m times some positive integer s. Does it help? Well, from here, if I divide by q, oh, excuse me, I'm a little bit jumping ahead. If I divide by d here, and I get m divided by d, which is q, so we are getting there. You see, our goal was to prove that this actually is the same as the previous set we saw before, the previous subgroup, this one here. And we are setting up that way. So let's suppose we have a subgroup of order D, and that subgroup must have a generator, and that should be R bar, and then that has order D, so D times that generator is 0 bar, the identity, and then we rewrite into modular expression. dr is congruent to 0 modulo m, so dr is m times s, be up to here, and then divide each by d. What do you get? R is m over d times s. M over d, what is that? That's q. We are getting there. We are getting to q. So R is qs. Oh yes, q divides R, which means R can be something times q, actually s times q in this case. So the generator belongs to the subgroup generated by Q bar. So the first subgroup must be a subgroup of this. Subgroup of this. But then again, they share the same order. R bar, this subgroup generated by R bar, is a subgroup of the subgroup generated by Q bar because the generator belongs to this Q bar. Here, it's got to be one of those, S times Q, so it's going to be one of those. But then again, they have the same order, so they must be the same. Consequently, oh yes, they're the same. Hence, if there's a subgroup of order D, then that's equal to this Q bar. So we prove the uniqueness as well. So that's the conclusion. So any subgroup, this time let me use a little bit more general expression. Subgroup H with order D, then that H is actually the cyclic subgroup generated by the Q bar. This way, I didn't really have to go through R bar in my final expression, but in the process of proof, I did require that R bar because this works for cyclic groups. And if you do not work out with cyclic group, this is not true in general. For example, if you consider Klein's 4 group, for example, then the uniqueness breaks down. There are multiple subgroups of same order. Okay, so much for A and B. And part C. Well, part C, do you recognize this formulation here? Have you seen this in number theory? And this problem is asking you to prove it. And I'm going to do that in a separate video, but I'll give you a bit of an association how things are going. So we are back here. So any subgroup of order D is actually a cyclic subgroup generated by Q bar. As a matter of fact, Q bar is nothing more than M over D bar, so it's going to be of this form. Now the second form is going to be a little bit more convenient, or maybe the third form. So let's write like this. Oops. Like this. Or if you prefer, you can rewrite like this as well. Okay, so when S is D, then dm divided by d is m, so that's 0. So whether s can be equal to 0 or s can be equal to d will not make any difference. But when you do some counting, the second expression can be sometimes a little bit more convenient. In particular, in this particular case, not everything here, not all fraction here qualifies as the generator. In the worst case, when s is 0, then we have 0 bar. That doesn't generate anything other than just itself, the identity. For which s value does this fraction generate everything in this cyclic subgroup of order D? Well, this s has to be relatively prime to D. In other words, this fraction, or this fraction times m, let me rewrite like this. This fraction times m, or like this. This fraction times m, and this fraction should be in the lowest terms. If it is not in the lowest terms, then you can simplify this fraction into smaller denominator, right? So with smaller number of multiplication, you're going to get multiple of m. So that particular fraction will generate a proper subgroup of H, not entire H of order D. So it'll generate the proper subgroup of some things, some order which is less than D, which is actually a divisor, but that's because of that Lagrange theorem. It should be a divisor too. So relatively prime and the lowest terms, well, those are related to Euler-Tauschen function. What is phi of n? It's the number of positive integers less than or equal to n that are relatively prime to n. And consequently, we are talking about those particular s's. And that's how this thing is related to the previous theorem. But that's where I'm going to stop. I'm going to do this part C in a separate video because it turns out it's a humongous work by itself. So for now, I'll say we are done with section 6, lesson 6, except for one optional topic. And see you again if you're interested. Otherwise, see you in lesson 7.